So hi everyone and welcome to our video on a deeper dive on the modern portfolio theory. In this particular video, we're gonna make some inroads on discussing a portfolio comprising of two risky assets. And we're gonna try and see if we can tackle a concept called the minimum variance portfolio. So this is again our extension and effectively a start to our discussion on the modern portfolio theory. So, what's in it for us when we analyze a portfolio of two risky assets, or if we analyze a portfolio of risky assets? Well, we may be faced with the scenario wherein it could be that a client is looking to diversify a single concentrated holding in one particular asset class. So, say there are, of course, portfolios that are out there that are just comprised of a single class of asset, maybe like technology stocks or oil and gas, natural resources, and so on, commodities, etc. And there may be clients or investors who would be willing to maybe add another holding and hedge against the risk of, say, one asset class bumming out for a year. So we have that sort of concept there. And two, you could potentially be a portfolio manager looking to add an additional asset to a pre-existing portfolio. Of course, you may have a good portfolio, a very diversified portfolio, but you could be looking at, of course, new stocks that may have entered the market. And when you add it could effectively lead to a better portfolio. So those are real world considerations that we try and factor in our analysis. So we have here the mean variance space, and the mean variance space has this asset representation. So we have here, for example, asset A. Asset A is here, somewhere there, and asset B is somewhere here. So what we notice is that mu1 is greater than mu2. So the expected return of asset 1 or asset A for that matter is greater than, so let this one be asset A, then we have asset B. So the expected rate of return of the asset A is greater than the expected rate of return of asset B. But we also see that higher rate of return comes at some cost. In particular, it comes at a higher standard deviation. So that's the standard deviation 1 is greater than standard deviation 2. So high risk, high reward, right? Essentially, that scenario. And points A and B show the expected return and standard deviation characteristics of the risky assets, A and B, respectively, or 1 and 2. So, what are the characteristics of a portfolio that is comprised or composed of two risky assets with portfolio weights X1 and X2 of asset 1 and 2, respectively? Well, as you hold X1 of asset 1, and X2 of asset 2 in a particular portfolio, then what happens is at the end of a holding period, you will receive essentially an X1 weighted return of asset 1 and an X2 weighted return of asset 2. Therefore, the portfolio's realized return ends up being this equation, which is just the weight times the rate of return of each asset. And the sum of that, you get that aggregate sum. Then the portfolio's expected return is essentially the expected value of this realized return here. Remember, the realized is already done with. When expected, it's still an uncertain outcome. Therefore, you just take the expected value of this, then you get your expected return. And then you note that both of these things are uncertain prospects. And we notate this as mu1, this is mu2. And we're going to be left with this formula here, wherein this is also unexpected value, all right, or an uncertain prospect. So, of course, while we do have the mean, right, we also have the mean or the return or the expected return, we also have, of course, the variance. And the variance can be expressed as something like this. So you can express it as this equation here, which will become ingrained into your head when we start discussing the portfolio theory. And this variance can be sort of generalized for a two-asset case in this manner. So that's essentially a typical representation of a variance. Again, just recalling basic statistics. And the portfolio variance represents the portfolio's total risk, right? And the total risk of a portfolio is essentially due to the contribution of an individual asset's variance and the contribution of the covariance as well. And note that we have the covariance. This one is essentially equal to sigma ij in some notations. And of course, by of course property, sigma ij is of course equal to sigma ji, right? So these two things are equal, should be regarded as equal. And of course, we do have this concept of the correlation coefficient. So if you recall, right, the covariance, we said the covariance can be represented in this way earlier, right? Sigma ij. Well, if you recall the formula, say you have two xy, the formula for a standard correlation coefficient, a Pearson correlation coefficient, is just this raw term. So say rho 1, 2, or xy in this case, rho xy. And that's just equal to the covariance divided by the standard deviation of each asset, right? In this particular case. So we can of course express the covariance, which is a sigma 1, 2, or xy in this case. So that sigma xy being equal to a rho xy, sigma x, sigma y, right? So we can express the covariance in that particular manner as well. So we can express that term, and that term, remember, is just the covariance of asset 1 and asset 2. So that's your covariance there, and mathematically, this is how we can put it in generalized two asset case. So um, we're gonna take now a deeper dive on the modern portfolio theory in the form of the minimum variance portfolio of two risky securities. So the MVP, so-called aptly named, right, is the combination of risky securities. So you have, say you have two risky securities that provides the portfolio with the lowest or the minimum variance among all portfolios that invest in the two assets. So it's the portfolio wherein say you choose two investments, say you have Apple, right? And then you have Chevron, right? Say you have those two investments, then you sort of play around with the portfolio weights, right? So say 0, then everything is here, say 0.5, zero point 0.5, say a 0.75, 0.25, and so on. You try and experiment with the different weights, and whichever weight combination yields you the least variance will be the portfolio composition, which ascertains or corresponds to the minimum variance portfolio. And the MVP of two risky assets is essentially the portfolio where changes in the variance or standard deviation with respect to changes in the portfolio weight of security one are 0. And we're going to show this graphically in another video. So on the MVP, since we know that the portfolio weights must sum up to 1, right? Then we know that if we're solving for another portfolio weight, it's just 1 minus the other, right? So we know that. Therefore, what we can do is, remember we had our equation earlier, mu1 plus x2 mu2. But we know that x2 can be expressed as just 1 minus x1 because, again, the two portfolio weights must sum up to 1. So we can rewrite both the portfolio expected return and the expected variance as these forms right here. Just a slight manipulation of the formula. So what we need to do is now to determine the weight of security one, right? Again, we want to find the portfolio with the least variance that gives us the least variance. Well, we need to minimize the portfolio variance with respect to x1 or the weight of portfolio one. And that's done using this particular derivative here. And if we do that, we're gonna get this form mathematically here. And if we simplify and solve for x1 in this case, we're gonna be left with this form of x1, which is this formula here, which is standard in the world of finance. And it's easy, of course, to imply that x2 is just 1 minus x1 MVP. So for us to get the the value of x1 that will minimize the overall portfolio variance, we need to use this particular form here. Okay, so that's pretty straightforward. So let's have an example to sort of make it easier for us to understand this particular case. So we're faced here with a problem. Okay, suppose we have two risky assets, 1 and 2, and they have the following characteristics. So we have expected returns of 17%, 12% for each asset, standard deviations 30% and 2% and 20%, and a correlation coefficient of 0.4%. Okay, this should be straightforward enough. The first question is find mu sigmas find the expected return of the portfolio variance and the portfolio standard deviation given the following weights. Okay, so that's simple enough. So recall, okay, for we have our weight x1 which is 0.75 and x2 which is 0.25, right? Well, we can easily get the variance. Okay, the variance is essentially, so if you recall, let me write down the given first for everything. So mu1 is equal to 17%, mu2 is equal to 12%. Sorry, we have now sigma 1, which is the standard deviation of asset 1 is 30%. Sigma 2 is the standard deviation of asset 2, which is 20%. And we also have a correlation coefficient of 0.4. Okay, so we have those there. So let's find first, okay, so finding the expected return. And for us to do that, we need to get, just actually simply get this using this formula. We have mu p, which is equal to the x1 times mu1 plus x2 mu2. So that's x1 is 0.75. Then mu1, that's 17%, plus x2 is 0.25. And then you have mu2, which is around 12%. And if we simplify that, so 0.75 times 17% plus 0.25 times 12%, we're going to be left with 15.75%. Right? So that's your expected rate of return of the whole portfolio. Okay, now let's now find the portfolio variance. So in order for us to get the portfolio variance, we need the individual variances as well. But you might see here, we were only given with the standard deviations. Well, we can easily get the variance by just squaring this term. So remember, the standard deviation is the square root of the variance. So the variance is just that squared, right? So sigma 1 squared is essentially 30% squared, which means that the variance of asset 1 is just 900% squared, right? Then the same goes for asset 2, sigma 2 squared. That's just 20% squared. And that's equal to 400% squared. So we have that one there. Then we can calculate, of course, for the covariance. And the formula for the covariance, sigma 1, 2, if you recall, that's rho 1, 2 times sigma 1, sigma 2. Well, we have rho 1, 2 here. And rho 1, 2 is equal to 0.4, right? That's 0.4 times sigma 1, which is 30%. Then we also have sigma 2, which is 20%. So if we have this one here, that's 0.4 times 30% times 20%, then we're going to be left with a covariance of 240% squared. Okay, and that's what we have there. Right, so we have a covariance of 240% squared, but of course, that is not your portfolio variance yet. Your portfolio variance is sigma p squared. The formula for this is x1 squared, then the variance of asset 1 plus x2 squared, the variance of asset 2, right? Sigma 2 squared plus 2 times x1, x2 times the covariance, right? So just plugging into our formula, right? So we're going to be left with x1 is 7.75. So 0.75 squared times 900, or your percent squared, plus you have 0.25 squared times 400% squared, plus 2 times 0.75 times 0.25 times the covariance, which is equal to 240% squared. And you'll notice all of this will be in percent squared, which is the traditional form for a variance. And if you calculate for this, this will just be 621.25% squared. And of course, we can find for the portfolio variance, and let's also find for the portfolio standard deviation, and that's just going to be equal to the square root of the variance. So sigma p is equal to the square root of 621.25% squared, and this will be equal to 24.92%, which is the right notation for a standard deviation. So that's how you get the portfolio variance and the standard deviation. Well, now, what you need to do now is we need to see, okay, so we were also asked, so this is number one is done. That's our first item. We were also asked, find the portfolio weights, the expected return, the variance, and the standard deviation of the minimum variance portfolio. So the minimum variance portfolio, of course, should have a lower portfolio variance than what we've had in number one, right? So because we're going to compute for that. So let's see what we can come up with. So 2, okay, so let's do it in green. Okay. Number 2, okay, the first step that you need to do is you need to solve for the portfolio weights. So solve for MVP portfolio weights. And your MVP portfolio weights are just, remember the formula x1 MVP is just equal to sigma 2 squared minus sigma 1 2 all over sigma 1 squared plus sigma 2 squared plus 2 sigma 1 2, right? And if we plug in what we have, so sigma 2 squared is going to be equal to 400% squared minus our sigma 1 2, which is going to be equal to 240% squared, right? Over sigma 1 squared, which is the variance, which is just going to be 900% squared plus 400% squared plus 2 times 240% squared. And if we get all of that, so the percent squared will cancel out. We're going to be left with just the proportion, which in this case is 0.195122, right? So that's what we have there. Then, of course, x2 MVP is just equal to 1 minus x1 MVP, which is 1 minus 0.195122, which is equal to 0.804878. So according to this math, right, the weights of the minimum variance portfolio, or the portfolio that will give the minimum variance, is that the amount of your wealth invested in asset 1 should be 19%, while the allocated amount for the asset 2 should be 80%. So that's a general that's how the allocation should be if you want the minimum variance. It's by no means saying that this is the best portfolio that you should get given your preferences, but this is the one that will yield the minimum variance, right? So we can calculate for the expected return, and the expected return is mu p, which is x1 mu1 plus x2 mu2, and that's just equal to 0.195 122 times 17%, plus you have 0.804878 times 12%, and you're gonna be left with 12.98%, right? Next, we need to calculate for the portfolio variance. So that's sigma p squared. So that's 0.195122 squared times the variance of 1. That's gonna be equal to 900% squared, right? 900% squared plus 0.804878 squared times 400% squared. Then you're gonna do 2 times each of the weights, 0.195122 times 0.804878 times your covariance, which is 204% squared. Right? Am I correct? That is 240% squared, correct? So if this happens, this should be equal to 368.78049% squared. Again, we can take the square root of this. So that standard deviation will be 368.78049% squared. And this should be equal to 8.68%. So just a few things to note before we end the video. Okay, it's clear that the minimum variance portfolio, which has this weighing scheme, okay, so the minimum variance portfolio has this weighting schematic, right, has a much lower standard deviation than this portfolio, which we just used as a sample above, right? So we have a 24% risk metric here. Now we have just around 9%. Quite a big difference. And it's something that we have there. Although I think square root of 306, oh, I may have miscalculated, sorry. So square root of 368.78049, this is going to be equal, sorry, to not 8.68, but whoops, this is going to be equal to 19.203% rather. So that's square root of 368. My apologies. So even then, you can see that 24.92 is much higher than 19.203. So that's how to solve for the minimum variance portfolio. And this is a deeper dive on the modern portfolio theory. In the next video, we're going to start to see various cases in terms of what we refer to as the investment opportunity set. So thank you for your attention, and I'll see you in the next video. Thank you very much.